Hello, welcome back to Larry's Classroom. We're going to begin our discussion today. We're going to talk about the Wheatstone Bridge. I'll draw you a schematic here of a Wheatstone Bridge. We got a power source. Our power source here will be a battery. The voltage isn't really important for what we're doing here. We got a resistor here, which we call this Rx. This is our unknown resistor, which we're going to measure with this circuit. Another resistor, which we can vary and is calibrated. This we will call RS, R in series with the unknown. We have a meter. We have another resistor, which we will call, we're going to call this R1. And another resistor, which we're going to call R2. We're going to call this branch A and branch B. As you can see, we have a power source. We have two parallel circuits. And then we have a meter, which is comparing the voltages at base. I'm going to call this point A and B. Well, let's call them C and D. We've already used A and D. C and D. So when we apply power to the circuit, we will have current I, well, negative positive, the way we hooked it up. So we're going to have some I total. We're going to have IA, current A flowing this direction. We're going to have current B and branch B flowing in the downward direction also. In this particular circuit, direction wouldn't matter, but we've set it up this way. We could put the battery either way. The idea is we have a calibrated variable resistor with a dial that reads out. So we have a known resistor here and known resistor here, so we know the ratio. R1 to R2 is a known ratio. Is known. And we're going to find the ratio of Rx to Rs, the unknown, to our series resistor, which we can adjust and read off the dial, which is calibrated dial on that resistor. And you can probably kind of see that this acts as a voltage divider when the ratio of Rx to Rs is equal to the ratio of R1 to R2. We will have the same voltage at point C as we do across point D, so no potential difference between C and D, no current flow, the meter is going to read 0. We're going to do a little bit of analysis of that. And we've already pointed out here that we're going to call this VT. Basically, Rx and Rs divides VT. But we also see that R1 and R2 divide VT. I'll write that over here. R1, R2 divides DT. Which we kind of talked about already. If they divide it equal, what's going to happen here is the voltage across Rx, VRX, the voltage across this resistor here, divided by the voltage across RS, we'll call that VRS, is the ratio is going to be equal to the ratio of the voltage across R1 divided by the voltage across R2. Now, we remember our Ohm's law where we said voltage equals IR, voltage equals current times resistance. We have IA here in this branch with RX and RS. We have IB in this branch with R1 and R2. So we're going to do a little bit of calculating with that. We're going to say that, we're going to do some substitution on this particular proportion that we've done here. VRX, well, that's going to be equal to IA times RX. So we can just substitute IA times RX. And that's directly from our voltage equals I times R. We've substituted that for VRX. And we can do likewise with VRS, which is IA times RS. And we're going to, the voltage across R1 is IB times R1, directly from our voltage drop formula, V equals I times R. So we're going to say that IB is times R1. That we replace for VR1. And we want, same token, VR2, the voltage across R2 is going to be IB times R2. IB times R2. So here we have got the voltage ratios. But you might note that we have IB, and IB is a factor in both the numerator and the denominator, so we can cancel that out. We have IA as a factor in both the numerator and denominator on this side. We can cancel that out. And that takes us to kind of where we started a few minutes ago. Basically says that Rx divided by Rs, the ratio of the resistances, is equal to R1 divided by R2. So when the bridge is balanced, when we have zero, when the voltages are equal, which we looked at the voltage ratios being equal, which gives us the same voltage on C and D, we have no current through the meter, no potential difference, no voltage read by the meter. We did a substitution for voltages. Now we've canceled out the currents. So when we have a balance on the meter, we have a ratio of the unknown to the calibrated RS, the same as R1 to R2. Now if we want to solve for Rx, we want to find Rx. We'll erase this here. We can multiply both sides by RS. RS here times RS here. Now, the RS is in the numerator and the denominators cancel out, so we're left with Rx, our unknown resistor, is equal to Rs times, let's move this down a little further, we've got a little more room here. Rx, our unknown resistor, is equal to Rs, our series resistor in the same branch as the unknown, times the ratio of R1, R2. So when we're using the Wheatstone bridge, we would read this off the calibrated dial. We would know this ratio from the resistors that we had in there, and there's probably an adjustable ratio arm that allows you to set this thing, but that you will be able to read that off the machine. You'll know all three of these values. It will allow you to tell what the unknown resistor is at the time that the bridge is balanced. When we have no potential from C to D, no current through the meter, or no voltage, depending on what type of meter you might be using, probably a voltmeter. The bridge is said to be balanced, and this formula will allow you to determine the unknown value. Now, before we leave the Wheatstone Bridge, I'm going to show you one other thing. This is not really anything new, but you might sometimes see the bridge drawn this way. The same VT applied. The meter here. And this would be our RX. This would be our RS, R1, and R2. And we'll have IA flowing around this way, flowing here, and IB flowing here. And this is branch A, this is branch B, and here's points C and D. Now this is exactly the same circuit, just drawn in a way that you're apt to see it with this diagonal square. We have the negative going to the junction of 8 and B, just like here. We have the positive, the other side of our power supply, going to the junction of RS and R2, just like we do here. We have our meter between point C and D, and point C is the junction of RX, RS. Point D is the junction of R1, R2 in both drawings. And this over here on the left side is the same as branch A, and this on the right side is in fact branch B. So we've you just often see it drawn that way, is the only reason I'm showing you that. But these are identical circuits, and it depends on balancing these ratios to get a null or a zero on the meter, and then you can read off the known values and calculate the unknown. We're going to talk a little bit about ground connections. You'll see several things in your home. You'll have what's probably a red or a black wire. And this is often called the hot wire. And you'll have another wire. I'm going to draw this with blue because I don't have a white pen, but this is usually a white wire. And we call this the neutral. Got 120 volts AC supplied here, BAC. And the neutral is usually tied to, we'll often see a ground this way, which some places they call that earth ground. We have another ground symbol you might see sometimes. They'll usually often call that chassis ground, but they get mixed back and forth. Some people call this chassis ground as well. We'll probably be using this the most, but this connection in your home would go out to your ground rod outside your house. I'll write that down here. And there's going to be a wire, a ground wire, goes to any device you might be using. Let's say you have a toaster. I'm going to draw kind of a awful picture of a toaster. Inside there's some heaters that heat your toast. I'm going to put them two in series. There's one on each side. Your slice of toast is probably going to go right down there. I'm only going to draw one slice here. And each of these terminals is going to come out of the toaster. I'm going to draw this one out here. And we have another one that's tied to the case of the toaster. I'm going to write case here. So Our hot wire is going to connect to one side of the toaster, one side of the element, and our neutral will connect to the other side of the element. I'm going to put a fuse back here. Here's a fuse. I'll draw it in green. Fuse or a circuit breaker. Okay, now you see here that the white neutral and the green ground are connected both to the ground back at the lighting panel where the power comes from. But here we see the green is only connected to the case. Well, these appear to be the same point. I'm going to put a couple stars on here. They're both connected back indirectly to the ground. Why do we do it that way? Well, in normal circumstances, both the neutral and the ground wire are at ground potential, which basically means your body is going to be close to ground potential. You're standing on the earth, you're standing on the floor of your home. So you could touch this neutral wire or this ground wire without getting shocked as long as nothing's wrong. Now, the reason that we don't just use a single wire is because of this. We've talked about IR drop. If let's say we had a not a very good connection here. We're not going to say zero, but maybe there's a little bit less than a perfect connection there. And let's say that this element burns out right here. We'll say it burns open. Now your toaster quits working, right? And maybe the broken wire reaches over and touches the case. The normal situation without this ground wire, now when we touch the case, we're touching the hot wire. Shock the heck out of us. But because we have this solid connection from the case back to the ground rod, we'll draw a lot of current through there. We'll trip the breaker or blow the fuse. We'll de-energize the circuit. This ground wire keeps the case at ground potential. I'm going to write that down here. This is an important thing. This is safety. Case at ground potential. That's the purpose of the ground wire, to keep the case at ground potential, which greatly reduces your likelihood of shock. Now you see that the neutral wire is connected to the same place. Why couldn't we just say, let's just tie the neutral to the case and not even have the ground wire? Well, as long as everything's good and fine, it kind of works. But that causes two things. You notice that a 3-wire plug can only plug in one way. You have probably seen some 2-wire plugs that are what they call polarized plugs. And you're basically, if we look at the end of the plug, we're going to have one longer one and one shorter one. So it can only plug in one way. Well, that keeps the neutral connected the way it should be if we want to use it for a ground wire. But if this ain't wired right, your receptacle ain't wired right, that can cause problems. If we have a little bit bad connection here, we can draw current through here. With our IR drop, we can still get a voltage there that might shock us. So we kind of got a double backup by using this ground wire that doesn't do anything else and keeping it solidly tied to the ground. And I guess the more significant thing about if you have a little bit of a bad connection, and actually let's not even talk about bad connection. In general, there's no such thing as a wire with zero resistance. So if we tied it this way, even when everything's working perfectly, there's going to be some voltage drop in that wire. It won't be zero, which means the case will be some small potential above the ground level. Where the ground wire, which normally carries no current, will never have voltage drop because You remember voltage equals I times R. If I is 0, V is 0. The ground wire only carries what we call fault current. And when this thing broke and sagged over to the case, as we said, now we have some fault current, and we could do the drop, the IR in the ground wire, we could have something other than ground potential, but by not using this wire for anything other than a safety ground to keep the case at ground potential, we greatly minimize our chance of having the case being other than ground potential. Talk a little bit more about grounds. And in the home wiring, the ground is very significant for our safety. We sometimes, and this might be the way your car might work, we might have 12 volts plus, minus, and we might ground this to the body of the car. And this goes out, maybe runs your radio, headlights, and gauges, and then they'll probably all connect to ground. So we end up using the body of the car as one side of the conducting path, and we also have a convenient reference point. If I wanted to read voltage anywhere in that automobile, I could put my meter on some convenient part of the body and I can start reading voltage with my voltmeter, the other probe. Now, there's nothing magic about this polarity. It's other than the polarity's got to match the way whatever your accessories are wired in, but you could have plus and minus. You could have a positive ground. Those standard in most American automobiles today is negative ground. I can't think of one that has the positive ground, but the circuit's going to function the same as long as you reversed all these. Well, the headlights don't matter. They're a light bulb. You can power them any way you want, but the radio and the gauges probably would need to be connected correctly. So whichever way the manufacturer designed this is going to work. We've kind of standardized on the negative ground, but it's not because the positive ground cannot work. It's just to keep things kind of on, everybody knows what's going on, I guess. Keep people thinking on the same page. We're going to look a little bit more at how we reference voltage to ground. We're going to draw us a battery. This is going to be 24 volts. Plus, minus. We're going to draw 3 resistive loads. R1 is going to be 8 ohms. R2 is going to be 8 ohms. R3 is going to be 8 ohms. Now we've drawn this with the negative terminal down here, and we have 24 volts. 8 plus 8 plus 8 is 24. Remember that I equals V over R. Current equals voltage divided by resistance. Well, 24 divided by 24 gives us 1 amp, and this is electron flows in that direction. I'm going to put some polarity symbols on each of these resistors. Now, we talked about a few minutes ago. So here we got current flowing through the circuit. We have 1 amp. So Each of these are 8 ohm resistors, so we're going to have V3 equal to 8 volts, V2 equal to 8 volts, and this is R1, V1 equal to 8 volts, and that's from this voltage equals I times R, our very common voltage drop formula. We took the 1 amp times each of the resistors. So we have 8 volts dropped across each of these resistors, and that does sum up to a total of 24 volts. And as we talked about a few minutes ago, in your automobile, a very common way of doing it is to add, rather than having this circuit be completed by a wire, we very often have a ground to the chassis of the car. And that gives us a couple things. Doesn't change the circuit any, but it allows us to put our meter on any ground, one side of it. Well, right here would be 0 volts. We move up there, we got that 8 volts there. If we read our voltage up here, I'm going to make some dots here to help you see these points. And I'm going to label them. I'm going to call this, I'm going to give you 4 points. Label them, we're going to call them point A, which is ground, point B, which is the junction between R3 and R2, point C, let's circle those two, point D, I don't put the A on the same side here. So if we were to put our meter, one probe of our meter, and being this is the negative side, we'd probably stick the negative terminal, which might be a black wire. We'll get you a black and a red here. So if I put that on any metal part of the automobile, if we read here, we're going to get 0 volts. We go up here, we went up 8 volts, negative, positive. That voltage drop across V3. Now if we go up to point C, we're reading both of these, 8 plus 8, we're reading 16 volts. If we go up to point D, we're reading this 8 plus this 8 plus this. Now we're at 24 volts. So we've referenced all of our voltages to ground by doing this. There are other possibilities. This is a common way of seeing things done, but there are other possibilities. If we connect our wire here and we put our ground on point B, what happens when we start reading things? Well, we'll put our probe here on ground. If we read point A, we went down 8 volts. We're going to see negative 8 volts. And a lot of meters nowadays will swing both ways or show you a negative or positive indication. So if you put your ground lead on the point B or on the chassis of the radio or whatever, read point A, you're going to see negative 8 volts. Go to another B, you're going to see 0 volts. We go up to C, now we're going to see positive 8 volts. We go up to D, we're going to see positive 16 volts. The voltages across each of the resistors are still the same, the still polarity. We just reference them to a different point. We reference them here. This one went negative 8 volts. Here we went positive 8 volts. Here we went another positive 8 volts. So we get negative 8, 0, positive 8, positive 16. Let's change our ground even one more time. Now we've created a positive ground system. We haven't changed our circuit any. Functions exactly the same. We put our meter on the ground now. Maybe this piece of metal is connected to ground. If we read at point C, now we went down from plus 24 down 8 volts. So we're going to read plus 16. 24 minus 8. If we go down one more to point B, we're going to have 24 minus 8 minus another 8. We're going to get minus 16. It's 0 here, minus 8, minus 16, minus 24. We're reading across the whole power supply when we did that. So sometimes where we put the ground is really just for a convenient reference point of where we want to measure our voltages, and stuff. If you see in a circuit a single point. I'm just going to, you probably haven't seen a transistor, but I'm going to draw a transistor here. You'll see lots of them, but suppose you had right here, it said plus 7, or yeah, plus, just say it said 7 volts. What that usually means, I'm going to change this to, is that is the voltage relative to ground, reference to ground. So I could take, if you just see a single number on the schematic, that pretty much means if you touch your meter to the case of the radio or whatever device you're working, you read there, things are working right, you should see 7 volts. So it's basically the voltage drop. You need 2 points. To get a potential difference, you need 2 points. When you see a single point, they're referenced to ground. So your potential difference is from ground to there, from the chassis to there. And we're going to talk a little more about what can go wrong with series and parallel circuits. We're going to draw a series parallel circuit, analyze it a little bit. Got a resistor, another resistor here. We got 120 volts supplied, and this is a DC circuit, minus and plus. We're going to call this R1, that's equal to 20 ohms. R2, this is equal to 80 ohms. And R3, which is equal also to 80 ohms. So we've done quite a bit of analysis of these type of resistor network circuits with power supplies feeding them. So we're going to take a look a little bit. Well, this is one with a series circuit in the main line. To figure out the total current, we need to have the total resistance. Well, we can redraw this as 20 ohms. And here we got two 80s in parallel, which we can replace with a single 40. So basically this 40 ohm resistor, I'm going to use a different color here. This 40 ohm resistor is the equivalent value of this piece right here. And we still have 120 volts. Well, remember our current formula, current equals voltage divided by resistance. 120 volts, 60 ohms is the total. We replaced this piece with a 40, but 20 and 40 is 60, so we're going to go I equals 120 volts, which we got from here, divided by 60 ohms, which we got by taking this 20 right here and adding it to the equivalent 40 of the two parallel resistors. And remember, these are equal, so we're able to divide them by 2. You probably remember that. R equivalent equals R over N. When R is equal, 80 and 80, they're equal. Branches, 1, 2, number of resistors in parallel. So 80 divided by 2 is a 40. But 120 by 60 is 2 amps. So we have 2 amps total flowing from this circuit. Flow in that direction. Now we could, an easy way to analyze this circuit, I'm going to get rid of this thing. It's kind of going to be in the way, I think. Get rid of most of it anyway. An easy way to analyze this circuit, 2 amps, 2 equal resistors are going to split equally. 1 amp, 1 amp. So everything's working perfectly. We have 2 amp, we're going to use this again, voltage equals IR. 2 amps, 20 ohms, we got 40 volts dropped across this resistor. I don't think I'm going to put the polarities on here this time. Not really going to matter that much. Well, here we have 1 amp times 80 ohms, 80 volts across that resistor. if we measure from end to end with our meter. 40 volts if we measure from end to end with our meter. And here we got the same thing. 1 amp and 80 volts. 1 amp times 80 ohms, is 80 volts. Everything's running just fine. What happens if we get a short? If we get a short, I'm going to label some of these points. Yeah, I think I will. I'll call this point A and B. A, B. If we get a short from point A to B, well, our circuit changes a bit. Then everything here is replaced with a wire. So what's left? We still have our 20 ohm R1. R1, I didn't label that. R1 equal 20 ohms. We have our short back to our power supply, minus plus 120 volts. So now what happens? We have, using the I equals V divided by R, we have 120 volts divided by 20 ohms. Now we have 6 amps. So we now have 6 amps flowing around this circuit in this direction. But what you might notice, R1 had 2 amps, now it's got 6 amps. It's got 3 times as much current as it had before. That could be enough to cause R1 to overheat and destroy itself. So that's one of the potential problems that can happen with a short circuit. And when we have maybe a wire fell across here or whatever, for some reason this become connected to here, and it should not be, we call that a short circuit. We have excess current, which we just calculated. But we can end up overheating R1. Now let's just say we got a break right here. And I'm going to redraw this circuit down here to look at it a little bit. Now our circuit looks like this. We still got R1 equal to 20 ohms. We still have, this is R2, why didn't I write that down? We still have R2 equal to 80 ohms. We still have our 120 volts. Now, originally, when we opened this up, this circuit can go away. So this is all that's left. So we have 100 ohms, 20 and 40, 100 ohms. We have 120 volts. I equals V over R. Our V is 120. Our R is 100 ohms. Well, 120 divided by 100, we have 1.2 amps. So now we have 1.2 amps. So what do we see here? We're having less current than we should have had. So some parts of the circuit may not be operating like they should, but you will notice this. Even though we have less current through R1, we still have the 1.2 amps through R2, which was originally 1 amp, so we have excess current through R2. We can have, even though we opened the circuit over here and reduced the current through R1, we increased the current through R2, and we could be overheating R2. Let's see what the voltage is across R2. We'll call that V2, and we'll use our voltage equals I times R, 1.2 times 1.2 amps. Let's put our units on there, 1.2 amps times 80 ohms. Let's see, that's going to be 80 plus 60, that's going to be 96 volts. So we have across here, and we're going to label this BA, we're going to have 96 volts, which we might write this as V. VA was referenced to B. VB. Let me get got that right. I don't want to lie to you. Yeah, we ain't quite there yet. But, so this was operating on 80 volts, now it's operating on 96 volts. We were over voltaging that part of the circuit, and we're actually under voltaging this part of the circuit, R1. VR1, we'll call it V1. And we got the 1.2 amps, or we have 1.2 amps now, 1.2 amps. We're using this same voltage equals I times R times the 20 ohms. So here now we have 24 volts. So this guy had 40 volts, now it's only got 24. This guy had 80, now it's got 96. So we're over voltaging this part, under voltaging that part, but 24 plus 96, 24 volts plus 96 volts, does in fact equal 120 volts. So our voltage total formula still adds up, just like I did here. 80 plus 40 was 120. But you can see that when we shorted here, we had too much current in R1, caused problems. We opened it up, we have too much current in R2, caused problems. So these are some of the things that can go wrong when you have shorts and opens in a series parallel circuit. Anyway, I think we'll call that good. Thanks for coming. Be sure to like and subscribe. Until the next time, keep on learning.